Hi all. Yes, it appears. Okay. Where's the page now?
Yes.
This one? Okay. At the meeting at Verona earlier, it was, I think, February, if I recall correctly.
Yep.
Paul van Reden had an interesting presentation, and on his slide he had written iterative method with G instead of G inverse. So I thought that catch my attention a bit. And I had also noticed a Wiese-Galp paper from some years ago by Jafar Rikia. And the title of that paper was a method for obtaining QTL solutions without inverting the IBD matrix. So here we have two points of interest of two pieces of work that talk about avoiding the inverse of a dense matrix. So if we think about a genomic model where we have SNP effects as well as a residual polygenic effect and a residual effect, we can represent the model with the equation above. And in terms of mixed model equations, we get the lower set of mixed model equations, where we have, of course, the relationship matrix, the genomic relationship matrix, and two variance ratios. Now, what we don't like about G is that it is a dense matrix. It doesn't have any simple pattern because many loci are contributing to the coefficients, and therefore it is a time and memory consuming to invert it, and at some point it becomes unfeasible to invert because inversion is a cubic process. So what we can do now is, if we take those mixed model equations, we can rewrite them as two simple equations instead of in a matrix form. And then if we know that Z1 and Z2 matrix are the same, we can simply replace them by Z to make the equations look a bit simpler. And then we notice that the first equation and the second equation have the same right-hand side. The right-hand side is always Z prime Y. So if the right-hand side is the same, it means that the left-hand side should be the same as well. So we can actually put these two equations together. The left-hand side of the first equation equals the left-hand side of the second equation, and then we get the equation written there. And this can be rewritten by simply writing out these multiplications. And then we see we have some multiplications that occur both on the left-hand side as well as on the right-hand side. Z prime Z multiplied with A, and Z prime Z multiplied with DGV. So what we can do is removing the redundant terms on the left-hand side and the right-hand side, and we get a much more simple equation. We have the variance ratio for the residual polygenic multiplied with A inverse multiplied with the A vector is equal to the variance ratio for the DGV multiplied with the inverse of the genomic relationship matrix and the DGV vector. So, and we said we don't like the G inverse because it's a computational issue. So we can multiply both sides with G, and then we can get rid of the G inverse on the right-hand side. It simply drops out on the right-hand side, and we get G on the left-hand side, but not inverted. So we got a relatively quite simple equation, and we have still these two variance ratios there, which are for the polygenic, the residual variance divided by the additive variance for the residual polygenic, and for the DGV, the residual divided by the variance of the DGV. And these variance ratios we can simply stick in in the equation, and we get that the DGV is directly related to the residual polygenic component, and we get a ratio in front, which is determined by the variance of the DGV multiplied with the G matrix and divided by the variance of the residual polygenic multiplied by the A matrix. So it seems like the SNP part can simply be computed from the residual polygenic part. And that would make things much more simple. And a way in which we could apply it would be an iterative approach to solve these equations. We can take an A vector and a DGV vector and set both of them to 0 and pick some values for the variance components. And then we can compute a vector of dependent variables corrected for the effects of the SNPs. And we can solve a set of mixed model equations where we fill in on the right-hand side the corrected y vector. And then from solving these mixed model equations, we will get the vector of the residual polygenic effects. And these can then be used to compute in step 4 the DGV. And at point 5, we can simply go back to step 2 and iterate the process until the solutions converge. So, in this iterative approach, it's an approach in which another iteration, step 3, is nested. So step 3 was the step where we solved the mixed model equations, so that's a separate iteration that is nested within this iterative process. But the inner iteration can be solved with a standard PCG solver, so it should be very quick to solve it. And the coefficient matrix that is used in step 3 needs to be set up only once, so it's not hard to do. And also the matrix in step 4, where we have the variance ratio of the DGV and the residual polygenic effect multiplied with the genetic relationship matrix and divided by A inverse, that component needs to be computed just once. So if we look this iterative approach again, it's really the two larger complications to compute need to be done only once. The outer iteration then requires only the computation of the corrected vector of dependent variable, as well as the DGV vectors, which are both computed as a matrix times a vector multiplication, and therefore these are not so complicated to compute, and then the calculation of some convergence criteria. So it seems that this model would be relatively simple to do. However, it only works if a residual polygenic component is present in the model. It cannot be applied in a model where one chooses only SNPs. And it might be more difficult if the residual polygenic component has a very small percentage of the variation. One idea could be to start with the residual polygenic effect, for example, at 25%, and then during the iterative process to gradually lower it to, for example, 10%, if that is your target. Of course, another model to estimate DGVs would simply be use SNPLib instead of GBLib. However, in SNPLib, that's a model without a residual polygenic component, or if you choose to add a residual polygenic component, then the equivalence between SNPLib and GBLib is not anymore quite there. I mean, we know from the Goddard paper that SNPLib and GBLib are equivalent, but that assumes that there's no polygenic component in the model. So here I try to explain that in a case of a model with SNPs and a residual polygenic component, the G-blub approach takes a weighting of the two relationship matrices and then inverses that. Whereas in a SNP-blub type of approach, one first inverts the two matrices and then weights them. So that's a different order of doing first weighting or first inverting, and that does not lead to the same matrix. Therefore, SNP-blub and G-blub, in my opinion, are not equivalent if there's a polygenic component in the model. Thank you all.